So we are going to start inter-process communication today, and we are going to see, we have done fork, we have done EXEC, and now we are doing pipe signals. We'll do later. There are four kinds of inter-process communication mechanisms that we'll be seeing in this session and the coming sessions. That's pipes, FIFOs, message queues, and shared memory. Okay, all the four IPC techniques are used to establish inter-process communication among processes that are executing on the same machine. Whereas socket streams and protocols will be using learning that will be used for inter-process communication among processes running on a different machine that requires a very good knowledge of networking and network programming. Talking about pipes, suppose you have two distinct processes executing as we did yesterday. Both the processes have file descriptor number 012 and 012, their exclusive list of process file descriptors. And now these two processes during their execution want to communicate with each other. Now, to establish communication with each other, the two processes need inter-process communication mechanism, and the mechanism that we are going to see today is pipes. We have to establish communication between these two pipes. We will need to create a pipe which will be a buffer, which will be a stream kind, not exactly stream, it will be a buffer, a kind of data channel through which the data will travel from one process to another process. If you look carefully, on one end of the pipe you will have the write file descriptor which will be performing writing into the pipe, and other end you will have to have read file descriptor which will be performing reading from the pipe, and the data will move across the pipe to the other end. Pipe is the only form of inter-process communication that are used on all Unix implementation, Unix, SPUX, Sun Solaris, IBM AIX, and whatever. Pipes are also used on all kind of operating systems that I know, including iOS, Android, Windows, Macintosh, Linux. It is used everywhere. It is the oldest form of Unix IPC. The primary attribute of pipes are two. One, that the pipe is half duplex. Okay, and another is limitation, that the pipe could be used only between processes that have some common ancestor. When I say common ancestor, I mean the first process and the second process should have a connect somewhere in the predecessor hierarchy. I'll give you reasons why it is so. The data moving through the pipe follows the first in first out principle. No element added at, all the elements are added at one end of the pipe and exit at the other end of the pipe. There is no way of an individual data to move ahead of another data inside the pipe. You can have multiple writers, multiple processes performing writing into the pipe. You can have multiple writers, but only one reader is suggested. But the reader will never be able to distinguish that which data is coming from which process. So we have these file descriptors 0 and 1 and 2. When you create a pipe, the pipe gives you two more file descriptors, a write file descriptor and a read file descriptor, two more file descriptors. The pipe is created in your system using a pipe system call. Look at the argument to the pipe, an array. The argument to the pipe is an array of two integers. In these two integers, you'll have two file descriptors stored. The zeroth index of the array after the pipe call is successful, it will return 0 for success, and the array will be filled with read file descriptor and the write file descriptor, both the file descriptors connecting to the pipe. It gives you -1 for error. So when you give the pipe system call, to which you give an array of size 2 integers as argument, then the pipe is created. The 0th index of the array will contain the read file descriptor, this one, that will read from the pipe, and array 1 write file descriptor, which is here, which will perform writing into the pipe. This is how the pipes are going to be created. The array is declared in the process. Now there is an issue here. Issue is, it's very easy for you to understand, fine, the pipe is a buffer and the size of the buffer is 64 KB. You declare an integer array of size 2, fine. You give the pipe call and the array as an argument, pipe system call will create the pipe, return 0 for success, and the array will be filled with two integers, the read file descriptor and the write file descriptor into the pipe. Everything is fine, but listen this carefully. The pipe is declared in the process. Which process? The process on the left or the process on the right? Pipe is certainly declared in, the array is certainly declared in one of the two processes. Say the process on the left. Now, array in the file descriptor are going to be in a single process, the array in which the two pipe file descriptors are going to be stored. Both the file descriptors will be in the array when the pipe call is successful. So, if you see this carefully, there, the array is declared maybe local to the main function, so it is in the stack frame, in the stack segment of the main function. Now, the two file descriptors that are created are local to this process. But what we want is the write file descriptor should be this side and the read file descriptor should be the other side. But what is the scenario is both the read and write file descriptors are right here in this process, where array 0 is the lowest available file descriptor number representing the read file descriptor from the pipe, and a write file descriptor is the next lowest available file descriptor performing writing into the going to be used for writing into the pipe. And the pipe have both read and write file descriptors into the same process, so the pipe appears to be emerging and converging into the same process. Instead of going to the other process, the pipe is coming back to this process only because the read write file descriptor both are in the same process. So the pipe U-turns in the same process. This is the issue. What we need to do is to solve this problem and make pipe connect with the other process. Is to solve this problem we use fork to create the child process. You did that earlier yesterday, and the child will do execl to invoke the other process, that is this is the other process, and share the pipe file descriptor, the read file descriptor of the pipe, with the newly exec'd process from child process. And now the new process will be independent process executing, and the new process will get the read pipe file descriptor as an argument, and the new process will be able to connect with the pipe using this read file descriptor, and then you can say that the pipe goes from here to here, and from here this process will be able to perform reading into the pipe using the read file descriptor which is shared from here. Okay. So that happens when you do fork and exec. You do fork, this process will do fork, and then the fork child will be created. Child will do execl and share the file descriptor from here to here. This process will be invoked, get the file descriptor, and this process now have the write file descriptor, this process now have the read file descriptor, and you can perform inter-process communication between two pipes. This is how the pipe is created. It involves fork, it involves execl, it involves creating a pipe, it involves sharing a file descriptor from the first process to the newly created process, and then you can start the inter-process communication between the two pipes, right? So creating a pipe using pipe call, and now once the pipe file descriptor is shared, you can now establish communication. Now communication could happen between the two processes. For the communication to happen through pipe, both the reader process and the writer process has to be connected to the pipe at the same time. It is not that the writer is connected and the reader will connect later on, or the reader is connected and the writer will connected later on. Both the processes has to be connected at the same time. Suppose the writer is connected, reader is not connected. Then the writer is writing into the pipe where nobody will read. This is considered an illegal operation, and kernel will send a signal called sig pipe. Like child used to send a signal, sig child to the parent to intimate the parent that the child is over. Now the kernel will send a signal called sig pipe and terminate the process that is doing illegal operation, vice versa. If the reader is trying to read from the pipe where there is no writers connected, the reader will never get any data. That's also considered an illegal operation. Kernel will intervene, send a signal called sig pipe and terminate the reader, considering that the reader is doing the illegal operation. So the pipe is like this. It has two file descriptors, the write file descriptor and the read file descriptors, right? If the writer and reader process are connected to the pipe at the same time, but writer is not writing to the pipe is empty, isn't it? What will the reader do? Well, in this case, the reader will see that the writer is present, but the pipe is empty. Reader will try to read from the pipe. It will see that the writer is present. As the writer is present, the writer may write sometime in future. So the reader will see that the writer is present. The reader will wait. Therefore, the reader will go on block on read. It will wait for the writer to write something. And when the writer writes, reader will read. Vice versa. The writer also writes into the pipe. Suppose the pipe is full and there is no place in the pipe to write more data. But the readers are connected. Because the readers are connected, writer will know that okay, readers will read in the near future. So the writer will go on block on write and wait for the reader to read something, and then the pipe will be having some empty space where the writer will be able to write anything. This is the concept of pipes. The pipes are internally implemented as circular buffers. That's why you've been studying circular queues, which you'll study next weekend, where the writers will keep on writing into the pipe and the readers will also keep on reading into the pipe, and the circular goes on and on and on. Okay. So we already have three file descriptors 0 and 1 and 2 connected to the standard input, output and error streams, and once you create pipe, you have the two more file descriptors number 3 and number 4 connected to the pipe. Okay. So let's see how the pipes are created. Pipe. Well, look at this line number 13. We are creating pipe using the pipe system call. An array of size 2 is given as integer. Array of size 2. It returns 0 for success or -1 for failure. If it is successful, then the array will be filled with two file descriptors. The read file descriptor coming from array's 0th index and the write file descriptor coming from array index 1. Let's run this and create our first pipe. There it is. 3 and 4 read file and write file descriptors were created. So the pipe was created. The pipe once created is actually a buffer of size 64 KB. This 64 KB pipe is allocated to your process as a resource. When the process will be over, the buffer will be deallocated and the pipe as a resource will also be taken away from the process and it will no longer exist. It will cease to exist. Have a look at this. We are creating two pipes. We have created two arrays, ARR and BRR. In the array ARR, we store two file descriptors after creating the pipe and then display the pipe file descriptor. It will display the file descriptor number 3 and number 4. The read and the write file descriptors to the pipe, and then we create another pipe and store the another pipe's file descriptors in BRR and print the other file descriptors, the lowest available ones. Could you tell me what will be the file descriptor numbers printed here?
5 and 6.
Very good. 5 and 6. Let's have a look at this. There you see. The first pipe file descriptors were number 3 and 4, and the next pipe file descriptors are number 5 and 6, as we expected. Yes, Jitinder? I think, Jitinder, you are mute.
Sorry, sir. Sir, I was asking, currently we are talking about a single process. The pipe is creating in a single process, right? Yeah.
That's right. Very soon we'll do fork and EXEC and pass the pipe file descriptor as argument, which we learned in the last class. Look at this. Again, we are creating a pipe, and the file descriptors are stored in the array called pipe1 of 2 integers. We print the pipe file descriptors 0 and 1. Okay. Then we open the file called test file and create the file descriptor number. Can somebody tell me what will be the file descriptor number connecting the file in the secondary storage?
5.
5, very good, that's correct. And then after that we create another pipe with 2 file descriptors, and the 2 file descriptors will be created and stored in another array called pipe2. Can somebody tell me what will be the file descriptor numbers for the next pipe? 6 and 7, very good, nice. So you understand how the pipes are getting created. There it is. 3, 4, 5 was the file descriptor, 6, 7 for another pipe. Creating a pipe and demonstrating that the pipe file descriptors are shared among parent and child processes. Let's bring in the child process now. So I create a pipe here. The array contains pipes read and write file descriptors. After that, we fork a child process. The parent, as it is scheduled by the scheduler, runs first. Here, prints the read and write file descriptors of the pipe. Break and run and go. The child will also print the pipes read and write file descriptor. Both the processes will print the pipes read and write file descriptors there, and this is a demonstration to you to prove that both parent and child processes have access to the pipe. There you see, both parent and child are able to print the pipe file descriptors. Therefore, we understand that both parent and child have access to the pipe. Implementing the inter-process communication between parent and child process. Because both parent and child processes are sharing the pipe file descriptors, so we can use pipe to establish communication between parent and child. So there it is. We create the pipe. The pipe file descriptors 3 and 4 are captured in this array. And then there is a data. Engineering is a religion of the modern world. Then we fork a child process. Now the parent executes first. Suppose the parent process prints the read and write file descriptors of the pipe, and after printing these file descriptors, parent process go to sleep for 10 seconds. The child process gets chance to execute. Child process executes the fork statement, returns Praveen, only Praveen. What will be the fork return when the child will execute fork?
0.
0, very good. So the child process will come to case 0. The child will print the read write file descriptors of the pipe, and after that parent will perform reading from the pipe. Have the parent written anything into the pipe till now? No. The parent has gone to 10-second sleep, and the child is performing read from the pipe. What will the child read and what will the child return? A read run from the read call. Can somebody make a guess?
It will keep waiting till the
Very
return
good.
is done.
That's the correct answer. But instead of terminology wait is for parent process waiting for the child process to finish. So don't use that terminology wait, okay? We will call block on read. If the pipe is empty, yes it is. The writer process is present, yes it is. It is in 10-second sleep. If the reader tries to read any data from the pipe that is empty, the reader will block on read. This concept is called block on read. But if you say wait is something related to parent-child. The reader will go on block on read and will wait for the writer to write. After 10 seconds, the parent will come out of sleep and write some buffer, a buffer of some length into the pipe. And then the parent will say wrote n number of bytes. Now the child will be able to come out of block on read, perform reading into this buffer, return the number of bytes read, print the number of bytes read, print the content that is read, child will break and exit. Then we are closing both read-write file descriptors of the pipe. This is another way of destroying pipe, deallocating the 64 KB buffer allocated to the process. And this pipe as a resource will be released.
So whether this block on read is indefinite or we can give a timeout?
It is indefinite. There is no timer concept in this. Yes, Jitendra?
Sir, you have mentioned that after writing section, read section will execute. How are we making sure that the before closing, after writing section, read operation will be called by the child? Like after 52, line number 52, you have mentioned that the read process will come into play from the child process context. But before that activity, if parent has closed the file descriptor.
So you're saying that there is a possibility that the parent may close these file descriptors and then the child process starts executing.
Yes.
So we'll see that scenario now. Let us try to execute this first and demonstrate block on read. Both parent and child are executing. Parent goes to 10-second block sleep, whereas the child has gone to block on read. After 10 seconds, when the parent will write, child will read. There it is. Okay. So this was a demonstration for block on read. Now let's do one thing. Remove these 10-second sleep from here and put it here. Now parent will write and go. Parent will write and then close the read file descriptor and write file descriptor, everything, and go. Then after 10 seconds, child will wake up and try to read from those pipes, from that pipe. Let's see. Parent have gone after writing 47 bytes into the pipe. After 10 seconds, the child is able to read. Did you see that? Parent went after writing. The child process became orphan process. The orphan process was adopted by systemd process. And after 10 seconds, the child came back from the sleep and was able to read. How is it that when the read-write file descriptor from the pipe were closed by the parent process, still the child is able to read from the pipe which is supposedly closed by the parent? Well, this was possible because of the concept of copy on write. The child had its own stack frame, own stack, in which when the child process was forked and created, then the whole stack frame of the main process was copied to the stack frame of the child process, which I told you earlier in fork. Now you have two set of file descriptors, one for the parent, one for the child. Parent closed its file descriptor, but the child still had its file descriptor connecting with the streams, further connecting with the pipe. Child was able to use that. That was a good question though. I hope you are able to understand that.
Yes, sir.
Very good. Whatever comes to your mind, whoever, whatever, ask me. Yes, Sachin.
सर अभी आपने स्लाइड में बताया था कि जो एरे में ओपनिंग एंड क्लोजिंग फाइल डिस्क्रिप्टर था वो सेम प्रोसेस के पास है.
हाँ.
ओपनिंग और क्लोजिंग फाइल डिस्क्रिप्टर. नाउ फोर्क करके हमने उसका सेम एक और कॉपी बना ली. दैट मीन्स जो ओपनिंग एंड क्लोजिंग फाइल डिस्क्रिप्टर है दोनों की ही सेम कॉपी आपके चाइल्ड प्रोसेस में बन गई है.
That's correct. So what's your question?
So the question is जो अब पेरेंट प्रोसेस राइट कर रहा है तो उसके पास रीडिंग और आई मीन रीड और राइट फाइल डिस्क्रिप्टर दोनों उसी के ही हैं या वो रीड अपना यूज कर रहा है और राइट उसका यूज कर रहा है चाइल्ड का?
Because of the copy and write concept, both parent and child have both read and write file descriptors. But the parent is using only the write file descriptor and child is using only the read file descriptor. That's happening right now.
एंड तो जो फाइल डिस्क्रिप्टर सेम है 4, जैसे 3 और 4 हुआ, आई मीन 4 रीड एंड 3 राइट, तो पेरेंट थोड़ा सा सर कंफ्यूजिंग हो गया.
No. Recall that concept of how the child was created in the stack segment. A new stack was created, new stack frame was created. So there is a 3 and 4 file descriptors in the stack frame of the main function, and there is a 3 and 4 file descriptors in the stack frame of the child process. Both child and parent process maintain their own set of file descriptors.
So that means कि child can also write to the parent.
Yes. Child can also write through the pipe. That's absolutely correct. Gaurav.
So is my voice echoing?
No, you are loud and clear.
Okay. So actually, my doubt was what Sachin sir asked. Can it be vice versa?
Yes, it could be vice versa also. So your voice is not echoing, but it is holding up a bit, as if you are sleepy, speaking in slow motion, something like that. No? I thought for a moment that are you drunk or what?
No, sir, feeling a bit sleepy.
So you are slow. Over that, the voice is also slow, huh? So let's have a look at this program. The parent closed the read file descriptor of the pipe while the child process was still able to hear. So we already had this, we have seen this, isn't it? So let's move on. So the reader tries to read from the pipe, but the writer doesn't write anything to the pipe. Instead, the writer closes the pipe and goes away. So what happened is we created the pipe, okay. The array contains the read-write file descriptor, fine. Then before the child process returns the child PID and control jumps to default and the parent executes. The parent process prints the read-write file descriptors of the pipe, but instead of writing, parent goes to 10-second sleep. While the parent process sleeps, the child process gets an opportunity to execute, returns 0 from fork, prints the pipe's read-write file descriptors and closes array 1, which is a write file descriptor. Now there are two sets of write file descriptors. One is maintained by the parent that is sleeping, another maintained by the child. The child has closed the write file descriptor. Now child have only read file descriptor, child does not have the write file descriptor. Parent have the write file descriptor, but parent is sleeping. Child performing read, but the parent is sleeping, parent have not written anything. Therefore the child process goes to block on read. After 10 seconds, the parent process comes out of sleep, doesn't write, instead closes the write file descriptor. Now child have already closed its write file descriptor. The parent have also closed the write file descriptor. So there are no write file descriptors connected to the pipe anymore. The child is trying to read from the pipe where there are no write file descriptors. So nobody is ever going to write into this pipe. Yes, Sachin?
Question was like when fork is happened, now same copy on write is there, but no write has been written, has been done from the parent. So still is the process is the same, or copy on write has happened. Like
the process is child and parent are two different processes executing in the same process context.
Yes.
In that same process context, you have two copies of read-write file descriptor connecting the pipe.
बट अभी सर मैं जब पढ़ रहा था कॉपी ऑन राइट में, उसमें यह था कि जब तक कोई बिट हम चेंज नहीं करते हैं, ऑपरेटिंग सिस्टम डजंट क्रिएट अ कॉपी ऑन राइट.
That's right. That's actually right. But what happens, even if, look at this, that is okay until unless there are some values, variables, holding values. But it is not true for file descriptors, because the file descriptors are not mere numbers. These are associated with kernel data structures like struct file, handle, and struct file. Okay, so these actually get duplicated. But what you've read is correct if you're dealing with only a is equal to some 55 value, some variables not connected to internal kernel data structures. Gaurav?
Are these file descriptors the default ones? 0 and 1.
No, we didn't. No, this is not the file descriptor 0 and 1. This is file descriptor number lowest available ones that happen to be 3 and 4 for us. This is array index 0 and array index 1, in which the file descriptor number 3 is stored, which is the pre file descriptor. And array index 1, you have the file descriptor number 4 stored, which is the pipe write file descriptor.
Okay, sir.
Yeah, please keep on asking questions, because things may get a little confusing. The only way to get through this is to ask me questions. Jitendra.
Sir, I am also a bit confused about this. As far as I recall, like आपने बताया था कि जब प्रोसेस exe कमांड हम यूज करते हैं, देन वी गेट अ प्रोसेस दैट इज रिप्लेस्ड बाय अनदर प्रोसेस, और उसमें हम अगर फाइल डिस्क्रिप्टर पास करते हैं देन वो एग्जिस्ट करता है बिकॉज फाइल डिस्क्रिप्टर इज एन एक्सटर्नल थिंग अपार्ट फ्रॉम द प्रोसेस कंटेक्स्ट। अभी मुझे जैसे आप बता रहे हैं कि यहाँ से हम फाइल डिस्क्रिप्टर क्लोज कर देते हैं, तो वो चैनल तो ब्रेक हो गया ना सर। सी करंटली पेरेंट हो या चाइल्ड हो, बोथ आर शेयरिंग द सेम फाइल स्ट्रीम पाइपलाइन। इफ एनी ऑफ देम क्लोजेस द पाइप, देन एक्चुअली वो पाइप ब्रेक नहीं होगा।
See,
That's
what
it.
happened is this is the process context in which the parent creates a child process. The parent creates a pipe. Okay, so when a pipe is created, suppose this is the pipe, and you had two file descriptors connecting with this pipe. Suppose this was your pipe buffer. So pipe is a circular buffer, so a circular buffer pipe is created like this. Suppose this white portion is your pipe. Okay, now two file descriptors got created, one the read file descriptor and one write file descriptor. Both the file descriptors further connected with the pipe. In your program, these two file descriptors were created and stored in an array, file descriptor number 0 and file descriptor number 1. This belongs to the parent process. Okay, parent created a child, so a new set of file descriptors got created in the stack frame of the child process. These new set of file descriptors are also numbered 3 and 4 for the child. Suppose this blue one is child, and suppose this was your parent. Now we have a common stream, but the file descriptors that are connected to this common stream belong to parent. So it was a read file descriptor and write file descriptor. When the child process got created, then you have another set of file descriptor for the child and for the parent connecting with the same stream. Parent closes the write. When the parent closes the write file descriptor, it closes its own write file descriptor. But another file descriptor, the child's write file descriptor, is still there. That's connected to the same pipe. In our program, the child has closed the write file descriptor. So It's the child actually closing the right file descriptor. Child is yellow. Child close the right file descriptor. Child is not going to write. Parent has the right file descriptor. Parent doesn't perform right. Parent doesn't perform. Parent goes ahead and instead closes its right file descriptor. When the parent closes its right file descriptor, the parent's right file descriptor is also closed. Now there is no right file descriptor. Nobody is ever going to write into this pipe. Nobody. Then, when the child performs read, it is going to read from the pipe where the pipe is already empty and there are no writers connected, so no data is ever going to come here. So the kernel will intervene and send a signal, sig pipe. Sig pipe signal. Which will terminate the child which is doing illegal operation. This is what I am demonstrating. Okay, so you'll see here the parent waited for 10 seconds and after that, instead of writing, closed the right file descriptor. So there was no right file descriptor. The child wala right file descriptor was already closed here, and the parent also closed its own right file descriptor. There was no right file descriptor in here. Yes, Sachin.
So that means, sir, कि kernel will kill this orphan child process.
Yes, that's right. Let's try this program. Kernel will kill through signal called sig pipe. Run. Now, parent is in 10 second sleep, child is block on read. After 10 seconds, parent will not write but close the right file descriptor and go. See what happens. Child is not able to do anything. Child is killed. Yes, Sachin.
Sir, what are the conditions which prompts the kernel to identify, okay, this particular pipe is happening a illegal operation?
See, pipe always belongs to the parent, to the kernel. It has allocated its access, given its access to the parent. The pipe was created by the kernel, and the kernel was the owner of the pipe, and the kernel allocated the pipe to your process. Kernel is watching how the pipe is being used. If there are any illegal operation happening on kernel's pipe, the kernel will definitely intervene and terminate the process doing illegal operation. Yes, Vipin?
So pipe is okay. I'm able to understand that pipe is a buffer and file descriptor is also okay. But how would you define a stream? Means that is connecting a file descriptor with a pipe.
Well, stream is basically a set of rules. Stream is basically a set of rules which describes how the resource will be used by some entity. Stream is a set of rules and kernel data structures to put together, which will also describe how the underlying hardware like buses through which the data will travel will be used by the resource and the entity. So a stream is not some hardware or so-called pipe or the buffer or the channel through which the data will travel. Streams are a set of rules that establish the usage, how the usage will happen, how the underlying hardware or whatever resource will be used by whatever entity. Inside kernel, the kernel maintains all the information about the stream as a set of rules and many other kernel data structures put together. It will also maintain, kernel data structure will maintain as a stream like access and permissions and usage IO on the bus. It will also keep track of the process that is doing using that hardware according to the rules set, the rules collectively called stream. I'll show you that kernel data structure now. So there is a kernel data structure called struct file. Here it is. This is the kernel data structure that represents stream, the path of the destination, if it is a file or a hardware device, its inode number, what are the operations that are allowed on that file, what is the lock mechanism, what is the number of writes, the flags giving you status, the access mode, the file position where the read, write, LC, whatever operations will happen, what are the security policies on that, the private data is empty field that is used by that device drivers when we'll write drivers will use it. What is the mapping of that particular hardware or particular file in the address space? Okay, and file handle is the file descriptor that acts as a connector to the stream. Okay, so there are I did not mention few other things like address space, like the hash list, the file array state, and one more thing, file operations. So these and the inode. These things actually are internal kernel data structures, which I'll tell you later, which give access to the hardware, which give access to the process, which give access to other kernel data structure describing the rules of communication. So there is this complex hierarchy of trees, a mesh of rules, routines, drivers, firmware coming together to make your data move from your memory out to the destination. And the destination could be some file in the secondary storage. Destination could be some other hardware on the motherboard or in your system. It could be some other device connected across the port, or it could be some alien system connected across the network somewhere. So this is the whole technology that we have to understand. I'll try to make it as clear to you as possible. Keep asking me questions. Okay, so you noticed SIG pipe, how SIG pipe comes and terminates the child process that do the illegal operation, right? So this was my preliminary discussion with you people on pipes. Keep asking me questions. I'll come back to you in the next session. I'll continue this further from here. I would request everybody only one thing. Everything is so interdependent. Whatever happens, don't miss these sessions. This is once in a lifetime. Things will happen to you. You learn. There is no concept of revising things here. You understand only once. Okay, and that understanding will continue